All right, good afternoon. How you guys doing? Doing okay? Ready for Thanksgiving? Okay, I'm still planning to grade and grade your exams and provide that feedback for you tomorrow. Tentatively 1 p.m. I'll email you probably in the morning or in the evening tonight. I spend a lot of time grading for the other class I'm teaching, so I'm further behind than I'd like to be, but I think I can manage tonight. And I still need to grade your homework, your second homework. So I will get you a third homework posted before Tuesday, and I will get your second homework graded before then as well. And if I don't get your exams graded by tomorrow, I will postpone the exam recap session to the weekend at some point. But my plan is to have that done, have them back to you, and then have the virtual session 1 p.m. So that's my aim. And today we've got more chlorination to talk about, and that'll lead us into advanced oxidation stuff. I think on the syllabus I had things slightly oriented differently, but I think this makes sense. So today I have way too many slides, way more than I could ever go through for you. So we're just going to go as far as we can, and it starts getting into the territory where I've done more and more of research topics, so it kind of just gets a little more fun for me, and I'll just keep talking. Except that we have a time limit, and that's good. And I forgot to bring my water bottle to work today, so I'm like potentially handicapped. So at least with my illustrations that I know draws a few giggles back there sometimes. Okay, so with that, we're going to get going and do what we can here. So last time we left off talking about chlorination, talking about free chlorine, the equilibrium. So just as a reminder, again, and I think we touched on it, but we will have an equilibrium between hypochlorous acid and hypochlorite, OCl minus. That'll look like this if we were to plot each species as a function of pH, where they find an equal point defined by our equilibrium constant, and this happens at around pH 7.5. So that means if we had, in our example last time, the pH 6, I think it was, for the poliovirus, we would see that something like 97% of the chlorine was in HOCl, or was probably, whereas a small portion of it would be in the OCl minus. And that becomes very in scenarios where we may have a sizable fraction of our chlorine in the useless kind, the OCl minus. And if we aren't careful and we treat water and it just happens to be pH 8 because that's what the river had, suddenly we have very little of our chlorine, or much less of it, maybe 20% of the effect that perhaps we designed for. Okay, so very important that we adjust for pH accordingly as needed. So we will often then apply disinfection for water treatment processes at around pH 5 to 6 range. That keeps us in a very nice situation where almost all of it is hypochlorous acid. So I'll give you a little practice here. This will guarantee we don't get through all 49 slides or however many I have. Take a moment and consider this scenario. If 15 milligrams per liter of HOCl is added to potable water for disinfection, the final measured pH is 7. What percent of this HOCl is not dissociated? Assume temperature is 25, which means we're going to take the Ka value to be 10 to the negative 7.54. So this will be a good check for you to recognize whether or not you're comfortable doing these equilibrium calculations, and if not, I'll do it quickly for you to give you some guidance on how you do this on an exam or homework or whatever. Hoping that at least if you had my class last year that you'll be good on this. Getting there or getting stuck? How you feeling? Excuse me. So I'll say a couple things real quick and then give you another minute or two because it looks like you're still working your way through it. With our equilibrium equation here, we essentially have two unknowns, but we should be able to find a system of two equations with one unknown, and therefore with two equations, two unknowns, and simplify it to one unknown, in part because the Ka is giving us a ratio between these two. Right? We know the pH, and so at a given pH, we know the ratio of OCl minus and HOCl. The question itself is asking for what percentage of the chlorine is in the HOCl form. That's kind of what I wrote up here. We can look at it as the not dissociated versus the dissociated amount, right? OCl minus is the dissociated form of free chlorine. Does that make sense? So the question is asking then, what is the percentage, which would be saying the HOCl divided by the total times 100%. So we have a couple of equations. We can get to this one based on the fact that the total, all the chlorine that we have together is HOCl plus OCl minus on a molar basis. So there's one equation, and we have the other up there. And if you wanted to put numbers, I thought I'll give you 2 more minutes and then walk you through it. I think that sounds correct to me. I haven't calculated it yet today, but even if we go back and take a look at pH 7, somewhere here-ish, if I drew that straight, looks like that's a pretty good range. Okay, feel free to keep working on it. I'm going to start my solutions and I'll talk you through it. said it was 77.6. Okay, so what you'll notice, what I did was, first of all, I got the equilibrium equation into a form that was expressing the ratio between OCl minus and HOCl. Then the other piece we can do is, on the flip side of this whole process, we can get a percentage of the total in terms of a ratio. Now that's intuitively obvious. If you know it's like a 2-to-1 ratio of one thing to the other, you could figure out in your mind there's some, A has some percent and B has the other percent. And for a 2-to-1 ratio, that means there's 3 parts total. So that should be a 67 versus a 33 kind of a deal. So intuitively, you know that there is some ratio that we can find there. Mathematically, we can take a look at this and simplify it by dividing the top and the bottom by HOCl. So that gets us 1 over 1 plus that ratio. And then we can substitute in from the equilibrium equation that defines that ratio. And that's 1 over 1 plus this 10 to the negative 7.54 divided by 10 to the negative 7, which even that simplifies to 10 to the negative 0.54, right? So putting all that in, we should get that 77.6. So this is one example. There are other scenarios where we might have to manipulate these. In this case, if we wanted to find the molar value of HOCl, we could do that, convert that to moles per liter, and then apply this 77.6% of it. Or perhaps we can even just leave it as, if we wanted it, milligrams per liter. So just a bit of a reminder, a bit of practice there for you, in case that was any trouble, to kind of refresh your memory. Okay, so I want to talk about chloramines. And speaking of equilibrium reactions, chloramines are an entire set or series of additional equilibrium reactions that we need to be concerned about if we have ammonia in the water. And sometimes this is very important, other times maybe not as much. So the deal is, if we have ammonia, NH3, it'll react with our free chlorine, HOCl, and give us monochloramine. Then the monochloramine, not mono, this monochloramine will be in equilibrium then with more free chlorine to give us dichloramine. And if you look at this, that is a NHCl2. So we've taken the ammonia, the amine, so to speak, and substituted 2 chlorines, and then we would have dichloramine in equilibrium with trichloramine. Now, this means that if we have both ammonia and free chlorine together, we will have some monochloramine, some dichloramine, and some trichloramine. These are a bit pH dependent, and typically monochloramine dominates, meaning we end up accumulating more of that. And it also depends on how much chlorine we've added relative to how much ammonia. Eventually, we will oxidize. If we keep adding free chlorine, we will ultimately oxidize even the mono, di, and trichloramines further and get us to things like nitrate. And then at that point, if we add more chlorine, we're getting free chlorine only because we've gotten rid of the ammonia. So if we take a look in these scenarios, take a look at the oxidation states. Oxidation state of the chlorine atom here. If we recall, the oxygen should be -2. We're going to ascribe that. The H should be +1. That leaves us with a +1 needed from the chlorine to get to the appropriate state. If we look at ammonia, each of these, the 3 protons is +1 each. So that means that nitrogen has to be a 3-. So if we then look at what's showing up over here on the right, well, essentially we're going to leave the nitrogen as a -3, each of these as a +1, and the chlorine as a +1. So chlorine doesn't actually change oxidation state. This is not a redox reaction. So it still has some oxidizing power because it would like to drop down to Cl-. It would like to take somebody's electron and be a little happier that way. So it's in the +1 state. So it's still an oxidant. And the combination of free chlorine plus any chloramines there are is what we call the combined chlorine. Excuse me. The set of chloramines is combined chlorine. Total chlorine would be the combined plus the free. So combined is talking about some nitrogen or ammonia has been combined with our free chlorine. So we have free chlorine that is not attached to ammonia. We have combined chlorine, which is some mixture of chloramines. Then we have total chlorine, which would be all of that together. Okay, and we typically have different test kits to measure those things. You can take a look over here at this plot. This is the dichloramine to monochloramine molar ratio as a function of how much chlorine we have. The more chlorine we add, the more we are driving it towards dichloramine at different pHs. So a bit pH dependent, but the more chlorine we add compared to how much ammonia we have, the higher the ratio. But it's not linear. It's driven by these equilibrium processes. We will still typically have a fair amount of monochloramine. Okay, this means that if we want to achieve chlorination for drinking or wastewater treatment, we have to handle a few things. And calling back to what we were talking about on Tuesday, first there are some residuals or some demanding stuff, some chlorine demanding substances that will exert a rather instant demand and react with our chlorine before we can make use of it for anything meaningful. So this would include many metals that are oxidized quickly, things like sulfide, which is why we use different sulfide compounds as chlorine removers or quenchers. And this would, if we had a significant amount of it, this would be hydroxylamine because it reacts quickly. So when we start adding chlorine, and we'll see at the very beginning if this is some typical water with some of these chlorine demanding agents, we will get no measured chlorine after adding maybe, let's say, 1 milligram per liter. So despite adding some, we measure 0. Okay, so that's going to satisfy, it's going to destroy or oxidize anything that's giving that instantaneous demand. After that, we have what we might call the combined residuals. So we are reacting with these ammonia compounds. So it could be NH3 by itself. It could be some organoamine that has NH2 or 3 in it. And then that's being chlorinated, so to speak. We're adding chlorines to it, making these substitutions. And we are getting some of these disinfection byproducts. During this phase, the more chlorine we add, the more we get because we're forming more of these combined chlorine compounds. It's not going to be necessarily linear. If we look from 1 to 4, that should take us from 0 to 3, but we don't quite get to 3 there. Maybe I'll do this on here. So if we were to add 3 units of chlorine, we would expect to be up at 3, But it's not going to be linear because some of it's still being demanded. Some of it's going to dichloramine, trichloramine, so it's not going to give a 1-to-1 ratio type of thing. You will have more than one chlorine go in that per molecule. So it's not an exact 1-to-1 ratio here. At some point, we have oxidized or reacted with all the amines that we can, and then we start going through a process where we are further oxidizing them and converting and actually making use of our chlorine. Let's say it would look something like this. We would have something like a trichloramine, so NCl3 plus more HOCl, going to, and I might try to balance this in a moment, going to probably Cl minus because we're achieving that oxidation, we're having the change in oxidation state, and something like nitride or nitrate. Okay, there's probably some steps in between to get all the way to nitrate, but if we take a look at this, if we balance the chlorines, we would have 4 on the left, so we'd need 4 here. The oxygens, we'd need 3 here. So maybe we should balance oxygens first, or maybe we're adding some oxygen or waters. So you could imagine doing a proper balance for this. I'm going to stop while I'm behind because I'm not saying this is specifically the reaction, and that's not my point. But it would be something along these lines, right? Where we are taking trichloramine and oxidizing it further to, and if we go back and look at the oxidation state of this, nitrogen went from a -3 over here. This is going to be a +5. Okay, so if we're oxidizing our ammonia from a -3 to a +5, it's going to take a lot of electrons, and chlorine is going to be the vehicle to do so. And it would be destroying that trichloramine. Okay, that's what's happening from B to C. And at some point, we've gotten rid of most of the chloramines. There's probably still going to be some in equilibrium because they just weren't all sent over to trichloramine and reacted. There's probably going to be some limitations there. And then that is what we call our break point. Once we finally reach a point where the more chlorine we add, instead of dropping the total chlorine that we observe, because this reaction here would drop the total chlorine, right? This is part of the total chlorine, and this is the total free chlorine that we're adding. So this reaction is getting rid of free chlorine and total chlorine, combined and total, to give us just Cl minus, performing that oxidation. So that's why our total chlorine here, residuals, are dropping the more we add. It's kind of a bizarre thing to think about, but we add more chlorine, we get less chlorine. But that's the nature of what we're doing here. From then on, we break through this breakpoint spot, and now we are doing proper breakthrough chlorination. This is where the term breakthrough chlorination comes from. We've broken through all that demand, all the ammonia-based demand, and now for every 1 milligram per liter of chlorine that we add, we're getting 1 milligram per liter of residuals. And we typically will see we have some remaining combined, meaning NH2Cl, NHCl2, probably very, very little NCl3. It's going to be mostly monochloramine here. But we'll have some combined residual, and then everything on top of that is our free chlorine residual. Okay? And that's where we have a 1-to-1 addition. So you'll see that slope is a bit sharper than the slope here. Okay, now at this point, we may still have some concern about reacting with organic compounds. Maybe this breakthrough scenario didn't really oxidize all organic chloramines, and we could even be forming with some organic compounds, forming more disinfection byproducts. So that's the scheme. That is what we call breakpoint or breakthrough chlorination. Does that make sense? Okay, so I don't know if we will, having 4+ equilibrium reactions does get pretty complicated. Probably not going to be taking this level of analysis, applying it to this system necessarily, but we might do some equilibrium equations to kind of see under one particular condition how much mono versus dichloramine might we have. Okay, so we might be making use of that equilibrium reaction kind of stuff, and I wanted to highlight how it ends up being important. This is also quite important for how we manage our disinfection and distribution systems, obviously for disinfection. By the way, these chloramines, they are somewhat reactive, but they're not nearly as strong as HOCl. I don't recall the exact numbers, but they are weaker. I think they're still stronger than OCl-, but they are not nearly as strong against most microbes in terms of disinfection capacity as HOCl. But in a sense, that's a little bit nice to have some of those in our distribution system, and sometimes we do that on purpose, so that it's a little bit longer lasting. Doesn't react quite as quickly with anything and everything, and it gives us a nice stable residual to keep some chlorine in our distribution systems. Yep.
Let's say, for instance, we're talking about the disinfecting microbes. In what region would you say we should keep the concentration of the chlorine gas?
Yeah.
What are some other things that we just have to think about?
Yeah, great question. So practically speaking, how much chlorine do we add to do a real disinfection in practice? Depends a little bit on the situation, but usually we will have a setup where we are applying more than we expect to keep in a distribution system. So we will provide a higher dose, and what we're going to do is dose based on the residual. So we're not going to dose based on how much we have to add, but rather dose based on how much we are achieving. Okay, so then what we will say, for example, the South Baton Rouge wastewater treatment plant, they apply 5 milligrams per liter of free chlorine for their disinfection step. And what they're going to do is they're going to measure at the end of their disinfection process to make sure that the lowest amount within their disinfection process was at least 5 milligrams per liter. Then all the math that goes into how well does that work is based on the most conservative case. Because you don't want to start with 5 and end with 4 and then try to have to average and see, okay, maybe I should do it 5.5 so that the average is 5 to get what we want. We want to be safer than that. We want to say at the minimum we have 5 throughout, because 5 is what we get at the end. So they apply at 5, and this is wastewater, so there's definitely some ammonia there. So they're definitely going through a breakthrough curve. So I don't know exactly how much they have to add, but from this graph, if it was the same, they'd be adding 10.5 to 11 milligrams per liter applied to achieve a 5 milligrams per liter residual. And if it was decaying within the 15-minute residence time or whatever they have, then they're going to have to add even more. Yeah, great question. Is that good? Any other questions on that? Okay. We'll just say if we had to add that much. All right. So, want to talk a little more about disinfection byproducts. Mentioned them a few times. Really, any halogenated organic compound would fall into this class. With natural organic matter or other dissolved organic matter, wastewater or whatever, there are thousands and thousands of different molecules. They have different moieties, different functional groups on their perimeters and just as part of their makeup. And so if we add a bunch of chlorine, we will be halogenating different pieces. So we already talked about the ammonia-based halogenations, but we could also have something like a methyl group, right? So normally this would be some molecule with a methyl group at the end. Well, with a bunch of chlorine, we could end up with something like this. This would be a trichloromethyl group. Now, it also turns out that if there is a lot of bromine in solution, HOCl will react with bromide and end up giving us HOBr. So we will end up with reactive forms of other iodide species, or other halogen species, excuse me. And those can be even worse because brominated things are more toxic than chlorinated things. So if we have situations like that, we want to be pretty careful, especially if we're doing something, let's say, with brackish or salt water. Now, that's kind of atypical for what we normally think of for water and wastewater treatment. Perhaps our wastewater, though, has a fair bit of chloride, and maybe there was some source of bromide addition. So then we might be concerned. Or if we are trying to treat, let's say, ballast water on a ship, and we want to disinfect it, and it happens to have water from an estuary, well, perhaps we don't want to be discharging a whole bunch of brominated hydrocarbons, right? That would maybe be a bad thing. So some of the classes would be trihalomethanes, this guy, trihaloacetic acids, and many others. And so we will monitor things like, especially the THMs and the HAAs, in a disinfection treatment process to make sure that we're not forming too many of them. So on a control aspect, a couple things we can do, even thinking back on this, we can recognize that these are going to be formed with more and more chlorine. If we put lots and lots of chlorine in there, then we'll have the potential to form more of them. We could also address the fact that we need a lot of DOM, dissolved organics, to allow this to happen in the first place. So if we can get rid of our dissolved organics, have some pre-treatment, perhaps then we will mitigate how much of these carcinogens we have in the drinking water, right? So either way, we can either design our system to function with a smaller residual, more time, but less highly oxidizing environment, could be a way to mitigate these disinfection byproducts, or less dissolved organics. This was actually one of the things that happened in the Flint water crisis. They didn't have adequate disinfection for the Flint River, and they ended up having issues because they had to chlorinate extra to meet the disinfection requirements, but then they were getting disinfection byproducts that were too high. How many of you have heard my Flint water crisis lecture thing? Anybody? A few of you? I was thinking about providing that after Thanksgiving. For those of you who have not, are you interested in hearing more about that? Kind of yes? Yeah? Okay, so I'll probably do that for the Tuesday after Thanksgiving. So if you've already seen it and are bored of it, just tune in for the last 5 minutes. Is a little update this year. There's a couple more legal things that happened. But I give it like often, so if you've had several of my classes, a few of you have, you're probably bored of it by now. It's my guess. So, little side note, but this was one of their many issues. It is a nice way to tie in, like, what are these redox? What's going on with redox? What's going on with the solubility? What's up with the distribution system? All that. So hopefully that's of interest, and feel free to let me know if you have any strong feelings about how we navigate that lecture. Okay, some more examples here. Kind of already mentioned some of these, but we could look at particular contaminants. So bisphenol A, this is one of those things in plastics, BPA, that we tried to get rid of because we were concerned about its pharmacological activity. So you could imagine that if we halogenate it, or if chlorine reacts with it, we might get particular disinfection byproducts from that particular one. So we can look at all sorts of different molecules and study, okay, how exactly are these being chlorinated, being halogenated, and what does that mean for their toxicity, for their stuff. So just kind of highlighting that. Okay, so that's kind of what I wanted to say about chlorination in particular. And so I've added those slides to this set of slides, which is ozonation plus advanced oxidation. So I'm going to try to get through ozonation, that kind of set of the slides. Like I said earlier, I'm definitely not getting through all of the advanced oxidation stuff. So you got some of that from Caleb as a guest lecture. So this will probably just be us getting through the ozonation and kind of take a look into all that. Okay, so ozonation has actually been used for a long time. First in about 1893, the Netherlands, later France, a decade or so later. And ozonation by itself is somewhere between an advanced and just a regular chemical disinfectant. Now, ozone itself is a pretty strong oxidant. So O3, right, you can imagine, you've probably heard, it is pretty good at cleaning stuff. It's pretty reactive. We don't like to breathe it because it's an irritant to our lungs. And it also absorbs UV quite well, which is why we like to have it in the upper atmosphere. Okay, it typically decays by reaction with water or other stuff a good bit quicker than chlorine would decay, but it's not like instant. So it'll hang out a little while. So we'll often apply it as a gas to water, and meaning we're going to have some sort of an aerated type of situation, but it's ozone that we're bubbling through. We'll use it for disinfection sometimes. It's pretty good against cryptosporidium compared to chlorine. The cysts are just simply not as resistant to it. It's also good for removing taste and odor, things like that. So you may have seen it before. You can actually get aerosolized cans of it as like a deodorizer, industrial deodorizer, to like just kind of wipe out any gross smells. You can use it for color treatment. Talked about the fact that, you know, some people like drinking brown water, but you usually don't like brown water coming out of your tap, right? So if you had a bit of tannins or something giving your water some color, and you obviously know that your consumers aren't going to like that, maybe you can use some ozone and clean that up. We'll also, like chlorine, it will be a pretty good oxidant for things like metals. And we can also, as we will talk about it, apply it in such a way where we are intentionally getting some advanced oxidation based on the chemistry. So a few characteristics. Ozone is colorless. It doesn't look like anything that we can see. It does have a bit of an odor. People describe it as metallic or a little sweet but pungent. It has a higher solubility than oxygen in water. So typically more like 450 milligrams per liter at 1 atmosphere. Whereas for oxygen, it's around, and actually I'm not sure if this is 1 atmosphere of ozone. I think this is just, would that be? So oxygen from our in equilibrium with atmosphere gets us something like 8 to 15 milligrams per liter, but only 21% of our atmosphere is oxygen. So we might multiply this by 5 to get, even if we do, we're still much less than 450 milligrams per liter. I'd have to go back and double check. This might be in equilibrium with 1 atmosphere of ozone, just pure ozone. Okay, at any rate, we typically will apply it at an amount of about 12% or less of ozone. It's actually kind of hazardous to handle, to generate. We usually generate it on the site. So we want to keep the hazards a little smaller, and then it'll also volatilize back out eventually. So that our practical limit is 2 to 3 milligrams per liter. That's more typical range that we will use. How do we make it? Well, there's a few possibilities. We can take clean, dry air or even pure oxygen. We kind of want to avoid nitrogen often because we could make nitric oxides, which could give us nitric acid, and that's pretty harmful for metals and people and stuff like that. So that's not so nice. So we will generally avoid any situations that can make that. And so I think that my notes are saying it's dry to avoid nitric oxide. I guess if we have water plus the process with this is a corona discharge, plus nitrogen gas, plus the corona discharge, that's probably where we get to nitric oxide. We're going to apply ozone to water, so it's going to be wet. But as we form the ozone, this is like taking an electric arc discharge, and if we do it right, we'll convert oxygen, O2, into O3. This requires a pretty large voltage. So this is 10 to 30 kilovolts. So if you're familiar with like a 9-volt battery, if you've ever been a little dummy and stuck your tongue on it, you're like, zap, right? You'll recognize that if it was a 9 kilovolt battery, you'll get zapped from like here, right? That's a very big potential difference. So you're getting a very big spark. Of course, that doesn't mean the current is huge, but you're going to get a very big zap. So the electrical hazards are present as well for you using that. So you put that across a dielectric material like a glass tube and expose that to your air. And then the frequency with which your electricity is pulsing, which is usually 50 to 60 hertz. For small applications, this is going to determine how much production we get. In some cases, if we need lots of production, we can even go up to megahertz ranges. Okay, another way we could create ozone is to use what we call vacuum UV. This is ultraviolet light that is something like in the 80 to 220 range, maybe just 200. I think people are calling 220 far UV lately. Maybe 180, I think. So 80 to 180, something like that, nanometers of the wavelength. If we go beyond that, we're really starting to get to gentle X-rays, gentle meaning the lower energy ones, or like extreme UV if you want to. I had a colleague in chemical engineering telling me that the industry of making some of the technology for like doing chip making, manufacturing, like electronics chips, got to the point where they have done so much X-ray lithography that people didn't want to like pay more money to fund more projects on X-ray lithography, so they started changing the name in the X-ray range of wavelength to extreme UV. So they just rebranded it so they could get some more research dollars. Anyway, so if we go low enough, we're getting towards X-rays, and we could go on, get to gamma rays and all that. But in the 80 to 180 nanometer range, we refer to this as UV light, but we call it vacuum UV because you need a vacuum for it to go anywhere, because oxygen is absorbing it so strongly that if you have any air in the system, it's going to be absorbed and it's going to be gone. That means we can use that and intentionally have the oxygen absorb it. And what happens when you have oxygen absorbing it, some photochemistry happens, and you'll end up with a fair bit of ozone. Okay? So we can intentionally generate ozone with UV of the right wavelength. It's not super efficient. Can't really do a huge flow rate of air with this. As you might see, if it's only penetrating a small way into the atmosphere because it's being absorbed so strongly, then we have some issue there potentially. But it does not produce nitric oxide, so that's maybe a plus. So we have a few ways to make it. couple others. I looked at this today. Unfortunately, this little video is really, really cool video. I'm sure it's online somewhere. NASA has a cool site. I just remember I included this because this particular video was the astronomy picture of the day, APOD. This was a little video of a lightning strike in ultra fast. It was really cool to see how it was going. This link unfortunately brings you to a dead video, but that page itself is still going, so they're still posting things. I'm sure you can find this somewhere, but I just remember finding this one in grad school and thinking it was so cool. So that'll date me if you look at that. Anyway, that's just an example of like the coronal discharge, all that. So we could do cold plasma, electrolytic. So a few other ways to make it. We can't really store it. It'll decay too fast, probably just decay into oxygen. I don't know, maybe you could figure out a way to get liquid ozone. It would be crazy expensive and probably dangerous. So no practical storage is there, so we don't typically use ozone except for when you generate it on site. Okay, so a few other things there. So let's take a look at a problem. And I might just introduce the problem, let you think about it a couple minutes, and maybe this can be practice, or maybe I'll sub this in as a homework problem. I don't know. I think this is from the book I use for the beginner class, so it's not so difficult, but a good example for how we might use ozone and what kind of calculations we might do. All right, so ozone is sometimes used as a disinfectant for drinking water. It's highly reactive, blah, 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 blah. It's found that its reaction with water follows nearly a first-order kinetics in terms of ozone concentration, such that it decreases by 50% in 13 minutes. So its half-life is 13 minutes. A water supplier wants to inject ozone into a pipe that's bringing water to the plant for some sort of a pre-disinfection effect on the influent. We have a 3-foot diameter pipe that is 3,400 feet long, with a steady flow rate, 10,000 gallons per minute. So the question is, what concentration of ozone in milligrams per liter should we inject at the beginning so that there will be at least 1 milligram per liter when the pipe exits into the treatment plant? And we can realistically assume it's like an ideal plug flow reactor. So take 2 minutes to think about how you might set this up. I'll make a couple comments and probably just leave you with this as a practice problem if you'd like to do that on your own. Okay, so I'm setting this up for you here. You can solve the rest of it yourself, but essentially what I'm proposing as the best approach would be to set up a mass balance to find, we're looking for the initial C naught. So we could describe from a plug flow reactor C over C naught is equal to negative K, e to the negative K tau. Tau, of course, is our residence time coming from the geometry of the pipe and the flow rate, so the volume over the flow rate. We could rearrange for C naught. It's not something we typically do, but there's no reason we can't do that. But the question then is, what is our K? And we need to get that from the information provided from the problem. And we can do so recognizing they gave us information about K when they gave us the half-life. So recalling what we learned earlier in the course, we can set up, again, using these type of kinetics, but this time just considering the time of decay in a batch type of situation, we can put in natural log of 1/2, so C over C naught is 50% of what we started with, is equal to negative K times the 13 minutes. So we rearrange that, we can solve K in per minutes, and then get all our units in the correct arrangements, and we should be good to go. All right. Good on that? All right. So, in practice, ozone contactors are a little more normally they're not so nice and clean as a long plug flow reactor. In fact, we usually have to bubble ozone into a reactor to provide a consistent amount. Again, in part because it decays, and in part because we're usually treating a high volume and not just in a long pipe like that other thing. So if we're bubbling ozone, we are inducing mixing. So whereas we might like to have a plug flow reactor, and we usually do that for a disinfection contactor, we have water coming in, it flows nice and smooth all the way throughout. Well, it turns out bubbling causes some mixing. So we might treat this as a system of CSTRs, where we have some barriers, maybe drawn like this, or maybe we also would add in some horizontal line. Kind of depends, but what we could then look at would be to achieve some relatively constant ozone. Some sections of these would be, the whole system would be better described as a series of several plug flow reactors, where we have, for tracking, let's say, some number concentration of microbes, we'd have our first section with a CSTR with N0 leaving out to N1. N1 then comes in, and then N2 goes out, and so on. And finally, N4 to N5. Sorry, I definitely did that poorly. I'm very sorry. I was like, as if it starts back on the, like writing a paper kind of thing. Let me make that make more sense. I mean, N5 is still the end, but we'd be going from here this way. So this would still be N1 to N2, N2 to N3, N3 to N4, and N4 to N5. So apologize for that. Point being, what's coming out of one segment is going into the next, and we can treat each of these segments as CSTRs in series. And if you recall, we've done this before. So if we have, let's say, first order decay of the microbes, that's our Chick-Watson kinetics, then our equation for this, if it's ideal CSTRs that we're using as modeling, if we take a look at N1 over N0, that should be 1 over 1 plus tau K. We're going to use K star because that will include the specific lethality with the ozone concentration. And so if we divide this up into equal segments, flow rate's constant, the volume of each segment is the same, we could conclude, like we've talked about before, if we just say if V1 equals V2 like that, then we could say N5 over N naught would be 1 over 1 plus tau K star, and raise this to the 5th power, right? Because it's 1 times the other, and just as a, make this nice and clear, if we did a sequence like this, and do this all the way out to N5 over N4, we would see many cancellations, like these two canceling, and so on, until we get to N5 over N naught. Okay, so that's how we can model. That's a little more practical, a little more typical modeling of an ozone contactor. So this time I think I will give you a moment to calculate this. So consider, let's just calculate. A, this system with a plug flow reactor, and B, this system as a series of 5 equal size CSTRs. So give that a go. Shouldn't take too long, I think. And by comparing the performance, let's just take performance as the amount remaining. Or, I don't know, maybe the amount removed, 1 minus that. All right, so we'll go through this with you. Had a chance to make some progress. So for A plug flow reactor, we're going to do our typical first, our batch type kinetics with tau instead of T. Find our tau's V over Q, should be 1,000 seconds. And we can solve for N over N naught as 4.46 times 10 to the minus 6. We have to convert our K into seconds, divide that by 1 minute per 60 seconds, multiply by that rather. But otherwise, things are pretty straightforward. And that's essentially a 6 log removal, so that would have been writing out 0.9999999 something, right? So pretty long list of nines there. For the part B, we need to recognize that we've just divided our volume by 5. So 1,000, or well, 100 divided by 5 is 20. Divide that by the 0.1 gives us the 200 seconds for the tau. And then use that tau in each of our calculations. Then N over N naught is 1 over 1 plus Kc tau, all that to the 5th power. That should come out to be 0.002 or 0.998 or 99.8%. So what we can see is we didn't quite make a 3 log reduction on our CSTRs, but it's very close. And the other one, we had something like a 6 log reduction for the full plug flow reactor. So it's not terrible, but it's certainly not nearly as ideal as we might had planned if we had expected this to be a pure plug flow reactor. All right, any questions or issues with that? Okay, so I think I only have 30 more slides to go, so let me just see if I have anything left to say about ozone before I let you go. Okay, and maybe I'll have to merge a little bit of ozone type of conversation with the Flint water crisis. So maybe I'll do an abbreviation. We'll see. Let me just do, we'll just do one more slide. You know what? This whole topic of how to do hydroxyl radical formation and advanced oxidation, actually, I think that's just going to, I'll save that for later. So that's it for today. I'll see you online maybe tomorrow or catch that when you like. Not here. I have a better lecture set up for at home. I don't have this room reserved or anything like that. So that'll just be online. And happy Thanksgiving. So see you, if I don't see you in a couple of weeks.